Welcome friends, we are discussing the AC network. We have discussed just the parallel AC circuits, where we have seen if we connect a capacitor in parallel to a choke or coil, the overall power factor of the system improves. Now in this part of this talk, we shall discuss some numerical examples. So let us consider this problem. In the series RLC circuit, say let us say we have a series RLC circuit. We have R, we have L, and we have C. So R is equal to 10 ohm. This is 10 ohm. Now XL is equal to 12 ohm. So this is XL, 12 ohm. So XL means L, when L is multiplied with omega, that will become XL, right? And XC is equal to 18 ohm. XC is equal to 18 ohm. So these three data are given. Current is 10 ampere. It is this 10 angle 0. So it must be connected across a supply. So this current is 10 angle 0. So what is, find the drop across each element and supply voltage. So find the drop across each element is like this. If this is resistance, then resistive drop is VR. Inductive drop is VL, and capacitive drop is C. So VR is just, the current is 10 ampere, so 10 into 10, 100 volt. So VR is 100 volt. Now VL is I into JXL. So inductive reactance is JXL. J is the operator. When multiplied, it will give a rotation of 90 degree anti-clockwise direction. So VL is that current into reactance J12, so it will be J120 volt. And similarly VC that is 10 into 18 ohm, that is JXC with a minus sign, minus JXC, so it will be minus J120 volt. So if this is the supply voltage V, so V is now equal to VR plus VL plus VC. So all those three needs to be added vectorially or by phasor. So when you added this 100 plus J120 minus J180, it will be 100 minus J60. So if you bring this into the polar form, it will become 116.62 angle minus 31 degree. So the supply voltage is nothing but 116 volt, 116.62 volt, but it is a lagging. If the current is 10 ampere, I is 10 ampere, 10 angle 0, which is reference, because 0 degree represent reference. So voltage is, voltage is V is 116.62 minus 31 degree. So this angle 31 degree, it is lagging. So voltage is lagging in this, because you see in this circuit, this capacitive reactance is highest. So this circuit is capacitive in nature. That is why overall current is leading. I repeat again, I am telling that it is observed that out of these three, R, XL and XC. XC is highest. XC is highest, right? So due to this fact, the capacitive or the circuit is capacitive in nature. The circuit is capacitive in nature. Now in a capacitive circuit, you know, current is leading type. Okay. So that is the reason voltage is lagging than voltage. So it conversely means the same, that current is leading than the voltage. So that is the result you are getting. Second problem we have, that suppose we have a figure 16. Let us say we have a parallel circuit like this. First we have a impedance Z1. This impedance is Z1, right? This impedance is Z1 marked by yellow. Which is equal to 2 plus J1. Z1 is equal to, this is Z1, 2 plus J1. So if you bring into the polar form, it will be 2.24 angle 26.6 degree. The second impedance is marked with green, that is 4 plus J8, that is Z2. That is Z2 for us. This is Z2. So Z2 is 4 plus J8. If you bring to the polar form, then it will be 8.94 angle 63.4 degree. And third impedance we have marked with sky. We have 3 minus J4. So we have a series RC, which is Z3. This is actually Z3. So Z3 is 3 minus J4. If you bring into polar form, then it will be 5 angle minus 53.1 degree. So in this way, we have evaluated all the impedances Z1, Z2, Z3. Now the current flowing through Z1 is I. This current is I. Current is I. Current flowing through the Z2 is I1, and current flowing through the Z3 is I2. So you need to evaluate I1, I2, I. If this supply voltage is 240 volt, 50 hertz, single phase AC supply. Single phase AC supply. So let us solve this. Let us say these two nodes are A and B. We have already defined what is node. So ZAB, that means with respect to A and B, you see Z2 and Z3 are connected in parallel. So let us say what is Z1 parallel Z2. The formula you know, Z1 Z2 divided by Z1 plus Z2. So if you solve this, now product, in case of product we use polar forms, and in case of summation we use Cartesian forms. So if you solve this, ZAB will become 5.55 at an angle minus 19.4. So therefore, expanding in the Cartesian form, ZAB is this 5.23 minus J 1.84 ohm. So if it is like this, then the equivalent network is something like this. So it is first of all Z1, which is equal to 2 plus J1. So this is 2 ohm and this is J1, and with this we have this ZAB. With this we have this ZAB, which is R and C. ZAB 5.23 real part, and reactive part is minus J 1.84. So effectively they are connected in series with the supply. So the Z equivalent is nothing but this ZAB plus Z1, that is series. So if you add them, you will get result as 7.28 at an angle of minus 6.6 degree. This is Z equivalent. So you know supply is 240 volt, equivalent impedance is this. So the current will be the supply current I, that will be, if you divide this, the result 33 angle 6.6 degree ampere. So 33 ampere is the magnitude, and it is making a 6.6 degree with the reference or the reference line. That is, if this is the reference line, then it should be the current direction. This angle is 6.6 degree. Its magnitude is 33 ampere. So that is the current. And now suppose if this is the current I, we have evaluated already, which is 33 angle 6.6 degree. Now after reaching at this node, it is getting two paths. One is along I1, another one is along I2. So I must be equal to I1 plus I2. I1 plus I2. So in this way, in this type of division, we use a very famous rule which is called current division rule. Current division rule. We shall discuss about this current division rule later on in the network theory module. So what is the rule? That is I1, you see we are evaluating I1, so let us evaluate what is the formula. I1, it is, let us say that I1 is the sum, in the numerator what is written, it is the 33 ampere, that is the total current. Total current into the impedance of the other branch. That means I1 is the, I1 flowing through the Z2. So in the numerator I must write Z3. What is Z3? Z3 is this value, 5 at an angle 53.1. So I am writing total current this into impedance of the other branch, that means 5 into minus 5, that means Z3. Okay, this is nothing but Z3, and in the denominator it is the summation of Z2 plus Z3. This is Z2 and this is Z3. So this is the rule of current division rule, and if you solve this it will be answer, it will be coming that 20.5 ampere with an angle of minus 76.2 degree. So this is the I1. In the similar manner we can evaluate I2 as well. This should be I2, not I1, sorry, I2. So I2, the same result. In the numerator it is first thing is total current into, now I am calculating I2, so the current flowing through this I2 is the current flowing through Z3. So now, what is the rule? It is the total current into impedance of the other one. So we must write Z2 here. So Z2 is 8.94 angle 63.6. You see, Z2 is equal to 8.94 angle 63.4 degree. And in the denominator, it is summation of two impedances. So if you solve, you will get this result, 36.6 at an angle of 40.3 degree. So I1, so if this is the reference line, so I1 is acting in this direction, something in this direction. Okay, it is minus 76.2 degree. I2 is acting in this direction, I2 40 degree, that means in this direction roughly. This is I2. 40.3 degree. So if you add this I1 and I2, I will be getting some value which is equal to this 6.6 degree. So this is I, actually this angle, very less angle, it is 6.6 degree. So this is phasor summation. So what is the current division rule? I repeat here. So it is the current flowing through any branch that is given by total current that multiplied by impedance of the other branch. Impedance of other branch. And in the denominator, we have sum of two impedances. This is the rule. And we will see this rule more in network theorem module in this course. Let us proceed to our next problem. Let us consider this problem, that is, we have V is equal to sine omega t, 100 sine omega t. So it is written as 100 angle 0 degree. And current is equal to, it is given 2.5 sine omega t minus 30 degree. So that means it is written is equal to 2.5 angle minus 30 degree amps. Okay. So the complex power, so you need to measure active and reactive power. Active and reactive power. So we define one term, complex power S, which is equal to P plus JQ. P plus JQ. Complex power that contains two parts. The real part is called active power, which is watt, and reactive, the imaginary part is called reactive power, which is var. So if you add this active power and reactive power, it will make apparent power unit only VA, volt ampere. So it is the common notation, and this is given by V, that is voltage into current conjugate. Voltage into current conjugate. So your voltage is 100 angle 0. So that is written. Now what is conjugate? Conjugate means this angle becomes just negative. So if it is a minus 30, it becomes plus 30. So I conjugate is written 2.5 angle 30. So if you add or if you multiply, it will become 250 angle 30 degree. So now if you break this component into cosine and sine term, so this 250 into cos 30 plus j sine 30. So cos 30 250 becomes 216.5 and sine 30 becomes 250 into sine 30 becomes 125. So your active power answer is 216.5 watt. It is not 125, it is J 125 because we have a J here. So this is the active component, real component. So active power, if you compare these two, you see we have evaluated here. This I am writing again. S is equal to 216.5 plus J 125. So if you compare these two, this with this, then this P must be 216.5. P must be 216.5 and this Q must be 125 var. So this is the solution. And alternately, we can do that, P is equal to VI cos phi. P is equal to VI cos phi. The angle is between 30 degree. So you can directly write V is equal to 100, I is equal to 2.5, and it is cos 30. That is exactly, it is coming here. 100 into 2.5, this 250 means what? 100 into 2.5, that is voltage into current, into cos 30, that is the real part, which is 216.5 watt. And Vi sin phi, same way, 100 into 2.5 into sin 30, it becomes 125 var. So S, that is complex power, has got two components. One is active component, is real component, it's watt or kilowatt, whatever. And reactive power has the imaginary component, or the reactive component is unit is var or kilovar, whatever it may be. Now we have another problem. It is the problem of power factor improvement. Let us solve. It is said that we have an industrial substation. Now in electrical engineering, we often come across this term substation. It is a very important topic or important term for us, for an electrical engineer. So with that, in that substation, we have a load of 4 megawatt. We have a load of 4 megawatt with a capacitor installed of this much, this rating 2 megawatt. Now to maintain the load power factor 0.97 lagging. So a capacitor. So what does this sentence means? A substation, a capacitor is connected to maintain this much amount of power factor. So it is quite close to unity. So we can say that this power factor is a very good power factor. Now what will happen to the load power factor when the capacitor goes out of service by some mean or by some way? If the capacitor is lost, then what will be the power factor? So we have already discussed this theory before. So we represent this phasor diagram again, this phasor diagram. Let us say we have a voltage phasor, and we have say that was actually initial current. We say that is a I coil. And the initial power factor was phi 1. So now if components actually are drawn like this, if the two components are drawn like this, one component is this component, let us say this component is OA, and another component is this component. Let me use some different. So another component is this component. Let us say this is AC. So OA, from this diagram we can easily write OA is nothing but this I coil into I coil cos phi 1, and AC component is nothing but I coil sin phi 1. It is quite obvious from this diagram. This is the OA component, this component is OA by green, so this must be I coil into cos phi 1, and this vertical component is AC by blue, that means this component is sin phi 1, right? So actually now what we will do here is that we will multiply both the terms with V. We multiply these both terms with V. This with V, I coil sin phi with V. We multiply this with V. So this V into I coil cos phi, so it becomes VI cos phi. It becomes VI cos phi. So now OA actually nothing but it becomes V into I into cos phi, or rather cos phi 1. That OA represents V, OA represents V into I into cos phi 1. Similarly, AC represents V into I sin phi 1. This AC represents this much V into I sin phi 1. Now V into I cos phi 1 is nothing but active power P, which is in our problem which is equal to 4 megawatt. In our problem it is equal to 4 megawatt. And AC is in our problem, it is nothing but VI sin phi, it is nothing but Q. Okay, it is nothing but Q, that is the reactive power demand of the coil. In contrast with the previous theory, this is the coil. So in this case it is the substation. So we can say this AC is nothing but the reactive power requirement of the substation or coil, maybe whatever. If you compare with the previous problem, it should be it should be coil. Now with this, if you come to this problem, it must be substation. So OA is the OA, you see base OA, it is written, represents the active power, and you see the AB, not AB, you see AC is it's the apparent power, reactive power. AC is reactive power, right? So OA is active power demand, OA is the active power demand of substation or coil, whatever you can say, and AC is the reactive power demand of substation or coil, whatever, but it is lagging in nature. Now, when the capacitor was connected, from the theory you can understand that this should be the diagram. When the capacitor was connected, our actual current was this. When capacitor was connected, so this was actually phi 2. Okay, so this current, let me use or let me say this point is B, let me say this point is B. So this BC actually nothing but IC. BC is nothing but actually IC here. If you compare with the previous diagram, you see. So this is BC actually to our problem. So BC actually IC. So BC is actually IC. Now if we multiply this with V, it will again become reactive, which is called BC. Actually it is called reactive power of capacitor, but it is leading in nature. So with this problem, what we can have here is that now the power system is operated at this point, B point, right? Power system is operated at this point, this phi 2. You see it is operated at 0.97 lagging. So if you take phi 2, it will be 14.1 degree. So this phi 2 becomes 14.1 degree. Now it is asked that if the capacitor goes out of service, so this phi 2 becomes now phi 1. So what will be that power factor? So with that we can directly write this equation is equal to, you see, this AB, okay, from this triangle OAB, from the triangle OAB, what we can write actually, from the triangle OAB, what we can write? You see, AB by OA, AB, this is perpendicular and OA is the base, it becomes tan phi 1, or no, not phi 1, tan phi 2. So with that we can straight away calculate AB, that is the reactive power demand, which is equal to OA into tan phi 2. OA is, you know, this is 4 megawatt. OA is 4 megawatt. That is the real power demand, 4 megawatt. Now into tan 14.1 degree, because this angle is 14.1. So if you solve this, we will solve AB as 1.005 megawatt. So this AB, this much AB, it is 1.005 megawatt, 1.005 megawatt. So this much is nothing but QL or Q load or Q substation, whatever it may be, 1.005 megawatt. Now BC is what? BC is the rating of the capacitor, as already mentioned here. BC is the reactive power of the capacitor, which becomes the rating. So BC is the rating of the capacitor, which is 2 megawatt. It is mentioned that is a capacitor of 2 megawatt installed. This is the statement, capacitor of 2 megawatt is installed. So this power is nothing but 2 megawatt. Where from this coming? Because when if you multiply this IC with B, it will become QC. IC into B becomes QC, that is the rating of the capacitor, which is equal to 2 megawatt. So if you add, now if you add AB plus BC, it will become AC. That means without the capacitor, now the demand is 3.005 megawatt. It was the actual demand. with the capacitor. Now if capacitor goes out service, it will become added 2, so it will become 3.005 megawatt. Now the new power factor phi 1, so from triangle OAC, from triangle OAC, we have what we can write, AC by A, which is equal to 10 phi 1. So AC is known, which is this value 3.005. O is known, which is 4 megawatt. So it will come out to be as 0.8 lagging. If you solve this, so new power factor is 0.8 lagging. So we can understand one thing, that if a capacitor is introduced, power factor improves. Now if a capacitor goes out of circuit, power factor falls. From, as we can see for this problem, is that initially it was 0.97, now it becomes 0.8 lagging. Now it becomes 0.8 lagging. So this diagram, actually this whole triangle is called, initially OA, it is the active power demand. Now we have OC and we have a OB. There are 3 different points. So BC is nothing but the rating of the capacitor. Rating of capacitor. So due to this capacitor, actually this is actually leading in nature. So that is why I am shading this one is, by green. This is this is leading in nature. This BC, that is the reactive power supplied by the capacitor. This is leading. This is leading in nature. Now when capacitor is not there, then the overall demand is this AC, this total entire thing, AC. Overall demand of the load or of the transformer or of the substation, AC is the overall, AC is the demand. That means the reactive power demand, not active power demand, overall demand of that load or substation, or you can say system, whatever you say. So on inclusion of BC or the capacitor, now the new demand becomes, you see this yellow, new demand becomes AB. So AB is the new demand. AB is the new demand. Of course, reactive demand of load with capacitor connected. And you have, this is phi 1, this is phi 2. So what we can write here is that AC by OA, that is equal to 10 phi 1. Again we can write AB by OA 10 phi 2. To equation, the rating of the capacitor, the rating of the capacitor, the rating of the capacitor is nothing but BC. Now BC is equal to AC minus AB. BC is equal to AC minus AB. What is AC? AC is equal to OA tan phi 1. OA tan phi 1. AB is equal to also OA tan phi 1. So if you take common OA, so it will be tan phi 1 minus tan phi 2. So the rating of the capacitor, you can write this expression tan phi 1 minus tan phi 2. So this is the rating of the capacitor or QC. So if you know your let us say the power system or electrical system is operated on 0.6 power factor lagging. Now if you need to bring your power factor to 0.9 lagging and your active power demand is 2 kilowatt or 2 megawatt, whatever it may be, you have this much amount of rating of capacitor needed to bring this change 0.6 to 0.9. you need this much amount of reactive power. So if you solve this equation, you will get some value of QC. So from there you can evaluate the value of value of capacitor, what value of capacitor you require to bring this change. So we have solved some problems with AC circuits, both series and parallel circuits, and we have also solved a problem of power factor improvement, where we have seen that power factor can be improved by adding a capacitor in parallel. It essentially injects a leading var to the system so that either it partially cancels out or neutralize the lagging var or fully neutralize the lagging var. So in this way we can bring the power factor from any value to unity depending on the rating of the system. And also at the last we have also seen that for a certain change, how much capacitor is needed to bring that change. We have also seen by that formula P into tan phi 1 minus tan phi 2. So with this I am ending here. In the next section we will see some more aspects of AC circuits. Thank you.